Hey everybody, Norm here. We've got a situation on our hands, and this time, quite literally. We've got a device that we're trying to make here. We're trying to make a very simple device that has a microcontroller, a wireless adapter on it, and then also a little 8x8 thermal camera that we talk to over I2c. You can see some crackpot wiring that I did in the back right there, but one of the things, by virtue of doing that crackpot wiring, I've got signal integrity issues, something that a lot of engineers tend to run into. So in this session, what we're going to do is we're going to dive into using an oscilloscope. Now, I'd love to go and start to use that one back there, but we're going to go a little bit more modern this time. I'm going to go ahead and upgrade to a PXI 1090 chassis. It's a little 2-slot job that we've got here. All we've got going into the back of it is Thunderbolt and power. And we got to be able to connect this to the computer to unleash the full power of PXI out of a single module in this chance, or in this opportunity. And we're going to go ahead and look at those signals real quick. All right, let's go. All right, so you might already have a variety of oscilloscopes in the lab to do benchtop debugging, but it's hard to get the power and performance that you can get from a PXI module like what we've got here. But how do you get started? What's the very first thing that you need to do? Well, presuming you've got a nice job like this with a 1090 or a nice chassis like this, like the 1090, a 2-slot, keeping it nice and compact, one of the first things to do after you plug it in is just to go to the hardware configuration utility and make sure that it goes into your system appropriately. Now, the hardware configuration utility is kind of the new version of Max, or Measurement and Automation Explorer, and basically because this chassis is basically a hot swap device, so you can plug it in when the computer's already on. You want to make sure that everything worked okay, and in this case it did. Let's go ahead and see what we've got here. You can see that I indeed have my chassis identified. It is showing up, and I have my oscilloscope available in the hardware configuration utility. Now, there's a couple other nice things that are worth noting in the hardware configuration utility as you select on the individual things. That's basically an upgrade over our previous generations. The one that probably matters the most to most of us engineers is the ability to go straight to the manual, specs, and pinout of the device kind of in a single click. And so that's really, really helpful. And we're not going to go ahead and go into it now, but rest assured, you click on specs, it takes you to the NI page that's going to launch, and you're going to see the specifications for the modules that you have right there. All right, so let's keep moving forward on this one. It's in there, it's available, and actually what we can do is we can go straight and click on soft front panel up here in the upper right-hand corner. You can see right there. So once we click on that, it's going to go ahead and launch Instrument Studio. Now, normally what I do is when I'm working with modular instruments, I just go ahead and open up Instrument Studio right away. It is a home for all of the soft front panels for your modular instruments and more. We'll get into that in future videos. But in this case, we're just going to go ahead and launch Instrument Studio launch, and it's instantly going to take us to a whole screen view of our oscilloscope, and we're going to see what we've got. All right, you can see it loading there. I've got that. And also another thing that I'm going to do right here is I'm going to go, let's see if I can go ahead and pull a split back on here. All right, so I didn't necessarily do myself any favors by wiring this in here so tight. And so as we saw before, but luckily I have my prototype board. So that's a very typical thing that any of us engineers may have and or see. And so I've already got a couple pigtails linked off here that I can go ahead and look into at least one of the signals for the moment. So I'm going to go ahead and strap this in there. Of course, I'm going to use my probe and go ahead and latch that on there. Now, while I do that and while I wait for things to get going, I wanted to note one very specific important thing that I just spent the greater part of probably 20 minutes trying to suss out. And I was using just a basic oscilloscope probe like this, but I was also trying to use a very simple one just like this here. And there's one very specific difference, and it's not because they're different shades of black, it's because of the ratio. This is a 10-to-1 probe, and this is a 1-to-1 probe. And of course, I'm going to be looking at small enough signals. I don't need to make my life harder. And so by simply using a 10-to-1 probe, I was looking for voltages at the wrong location because I didn't realize I had that in my system. So word to the wise, if you're going to be using an oscilloscope, seasoned veteran or just getting out there, don't forget to check the attenuation on your probes. And some of them, like the one I have here, actually have a switchable state, but I think those are actually outlawed now, interestingly enough, where some electrical body has decided you're no longer allowed to have a 1-to-1 and a 10-to-1 switch. So if you've got those and you like them, keep them handy because they're about to not be easy enough to find if you want that easy to switch between 10-to-1 and 1-to-1. And heaven help you if you find 100-to-1. But let's get back to the story at hand. Instrument Studio is up, as you can see here. We've got the signal already tapped into, but one of the things that we're not seeing is we're not seeing any digital data. Well, don't forget, we need to go ahead and kickstart the device. So I've got my little program here written in LabVIEW that's going to go ahead and take that 8x8 information that you can kind of see down here and interpolating it to something a little bit bigger, and you can kind of see my hand move across the page right there. So very nice. We've got things, and of course in the background we can see things flickering along. Now with oscilloscopes, another thing to really keep in mind, and let me go to one thing that's really important is the triggering setup. The minor point, let's go ahead and give ourselves the maximum amount of display here. Now we see it flickering around quite a bit here, and some of the things that we know that are important to realize is that we need to set up our triggering appropriately. And so usually if something's flickering or fluttering around on an oscilloscope, you've got to go ahead and tweak that. So for Instrument Studio and PXI based instruments, you're going to go ahead and look over here in this section to the right, and we're going to choose the one that makes sense for us. Now indeed, we don't have a digital line saying when the start of the burst is. Hysteresis is more about things moving into and out of a frame, but the thing that we really want is a window, because if I can look at my traces as I see right here, one thing that I know is that during the idle time between the packets, I have a window that basically my signal sits in between. That's that 3.3 volt rail. And so now what we've got the ability to do is go ahead and change that, and we're going to go ahead and deliberately set that window. And you'll see that when I set the trigger style to window, you're going to see some more things hop up down here in the bottom. All right, so now that I've gone through and I've gone and set up its window, you can see that we have two very new values there, window mode entering and level 1 and level 2. Also, you'll note that there's two different cursors that you see over here on the right, giving you the ability to set what that window is. Well, what we were trying to do is actually find out when it leaves that so that we can grab this burst of actual information. So let's go ahead and do that. So I'm going to set it to leaving, and then I'm going to go ahead and set my level 1 and my level 2. And now what happens is when that gets locked in there, we should see that. Actually, let's go ahead and set it to normal as well. And now we can see a very crisp view of that signal as it goes. Now we see a little bit of jumping over here to the right. There's some very good reasons for that we'll talk about in a moment. But a few different things that we want to be able to do is, once again, this is just helping you learn how to do this, use the oscilloscopes with an eye, is using that scroll wheel. Using that scroll wheel allows you to kind of get that bigger view, but you have to be careful, because what ends up happening is as you do that, the other thing that happens is you lose a little bit of that sample rate. Now there's a way of fixing this so that you maintain the high sample rate and also long record size. It's a little bit of a different feature than your common oscilloscope, but we're going to go ahead and move a few things around. All right, and the way that you would go ahead and move that trigger is basically you open up the window by, I'm just scrolling my scroll wheel down here in the bottom, and you can see that it opens up that window up top to allow for all data that's been acquired, all of the records. And at that point in time, basically I can move that trigger all the way at the beginning. Now we can go ahead and see basically the relationship from burst to burst to burst, kind of the timing in between them. We can set it to a single acquisition. And of course we can choose that mouse wheel to scroll back in to figure out where that burst is in my system. All right, now what's happening in here? Is this really the root of my problem? Well, let's go ahead and once again, get that scroll wheel, move it on in. We're gonna go ahead and just keep looking in. And you can see very quickly, my digital edges are not sharp at all. And I've gotten advice from others within the LabVIEW community and other engineers, hey, you need to put maybe a 1 kilo ohm or a 10 kilo ohm resistor between that digital line and the rest. Now, another thing that we want to be able to do is we also want to look at the relationship of the clock to that signal as well. So I've got another scope probe in here. I'm going to drop another line on the signal over here, and we're going to see what that looks like. All right, now a quick note on what I said earlier is that the clock line, no, this is the clock line that we're looking at. I2c has a unique ability. It has two major lines that you need to communicate with, one of which is the clock, and then the other one is the data. But indeed, these are the clock edges that are going, and so what I want to do is I actually want to look at the data edges as well. So once again, with NI oscilloscopes, how do you go ahead and do that? Well, I've already got the one channel in the system, so I'm basically going to go down here into the bottom left. I'm going to go ahead and turn that channel on that you can see down there. I'm going to go ahead and configure it volts per division, basically leaving it the same configuration that we had just a moment ago, and that's what we're going to look at. All right, so now we can see that we have the clock edges. I'm not seeing any information, so let's go ahead and do a little bit of debugging. All right, so we're back up in business here. It seems to be that when I've been connecting and disconnecting, it's been causing some spike to run through the system. Now I'm basically going straight wire into my microcontroller, which kind of makes sense why I'm having such these issues. So if you're working with the system, trying to create something, beware of that situation and don't be surprised. All right, so now we've got it in there. We're not hot plugging something into our device, and we can see, let's go ahead and get that trigger set back up. So we're gonna go once again back up to that window. We're gonna go ahead and set that in there. And indeed, it looks like we've got a nice stable trigger, mostly happening at the middle. Let's go ahead and use that scroll wheel feature again to go ahead and get those triggers set. We're gonna go ahead and have the trigger set for, I may have swapped signals on me, but I think it is, yeah, channel 0 is in yellow. You can see that because it's highlighted down here as the yellow indication. Oh, not that, like that. In the yellow indication, that is channel 0. And then we can actually set where that 0 offset is right there. That's fine. And we're gonna go ahead and move that up a little bit more. We're gonna put our clock in the bottom and then our data up top. So there's a chance I might even have a bad probe here. So let's go ahead and see what it turns into. So I'm gonna go back to kind of immediate triggering on the system. It looks indeed that I've got that. I'm gonna go ahead and change my, my trigger to go back to window, but I'm gonna change it to channel 1. All right, so now it looks as though my probe is okay. Now I wonder, is it the other channel on my oscilloscope here? All right, so oh. That is some very unexpected behavior from my system here. It makes me want to go get a different probe. All right, so one of the things that I'm going to do is I'm going to go ahead and say that this second probe, actually that's this probe right here that is going to the data line. I'm going to go ahead and say that that might be, it's suspicious to say the least at the moment. It's causing me some problems. So one of the things I'm going to actually do is I'm going to back up. It's going to have a little less signal integrity, but it's going to be pretty simple. It's basically a BNC breakout. And so I'm going to just try to do this, and it kind of takes a little bit of the, actually that 10-to-1 switch in the system that might actually be flickering on and off could actually be our problem on that scope. All right, so we're there. There's my hand again, moving back and forth across the screen. I can see what I've got, and there we go. Now our signal seems to be pretty stable. So I should probably throw that probe right into the trash. Honestly, we're gonna monitor it for just a little bit longer, but we're probably gonna throw this into the back. All right, so now that we've got a much more stable acquisition of our signal, now the question is how do we start looking at this? How do we find out what is the best resistance to put in as a pull-up on the system? So let's go ahead and do a little bit more experimentation. Once again, using our scope, Instrument Studio, and basically being able to look at the signals that we've got here. And maybe we'll even go back and investigate that probe to see how quickly it drops off and what its overall behaviors were. Okay, so let's kind of flash forward a little bit here to what I was able to do. So I've got a little potentiometer in there, and I've got it basically going to my 3.3 volt rail, and then I'm hoppering that over into the what is the data line currently. So if we go and we look at it a bit side by side here, so basically what I've got here is I've got the 3.3 volt rail going over to that device, and then basically going through our pot, basically pulling that line high to give the whole system a leg up. And you'll see is that I decrease my resistance on that line, which is probably high. I haven't measured it yet. You can slowly watch those edges. Oh, let's go ahead and reset the system and try again. All right, so now we've got it going. Let's go ahead and find that point where it's not going to flake the whole system out. Maybe I go a little bit slower, and we start to try to figure this one out here. All right, so I'd say those are pretty sharp edges. I can kind of tweak. Oh, there you go. You can see the DC bias come up on the bottom. So let's go ahead and say that that's probably good enough on both of these lines. Now, the reality is what I want to do is I want to get this actually on the clock as well, because if I'm straightening up my my data, but my clock is not acting correctly, I'm going to end up with exactly the same kind of issue that I had just a moment ago. Okay, quite a bit of interesting behavior here. One of the things that I'm finding out as I've been messing with this and rebooting it over and over again is one, I can't take the same resistor and drag that, the pull-up resistor, and drag that over. Everybody needs their own unique one. Makes sense, electrical engineering norm. I do have a degree in it, just haven't thought about some of it in a while, at least from these lower frequencies. So let's go ahead and get this set up appropriately. But the first thing that we need to do here is I have a resistor that I don't know what its current resistance value is. I just have tuned it in so that it looks okay. A few different things you can probably note on the actual signal itself, let's get them separated here, is that now if I were to kind of draw a bit of a line here, you can see that the bottom of it has pulled up from from 0 volts. Now, for me at the moment, that's okay because now I have that sharper edge up top. And so I kind of find that medium, as long as we make sure that it's got nice, crisp thresholding lines between the two parts of the signal, I think we're going to be okay for this. Now, the other part that we know is that, of course, you can very clearly see the skew happening on that data line needing that pull-up. So let's go ahead and try to figure out what's the right resistance. I've got a bag of tricks right here in front of me. We're going to go ahead and measure that. But here's one of the things of what we're going to do. We're going to go through and actually take advantage of the fact that I have an extra open slot in my chassis. And so without any extra room really on my desktop, I'm going to slide in a DMM. And I'm just going to go ahead and measure that directly and see what we get from within the exact same interface within Instrument Studio just by turning on a DMM tab. So let's go ahead and see what we've got. Now, a few different things for shutting off our 1090 chassis. It does have a small button in the back that should give us the ability to disconnect it before pulling out the Thunderbolt and then also shutting it down. All right, so I hit that little button on the back for the power. I'm gonna go ahead and disconnect. Actually, let's go ahead and shut down Instrument Studio here. I don't need this anymore because I don't wanna leave this on. Actually, I could probably leave it open. Let's just go ahead and remove that specific pane from the overall system. I'm gonna disconnect the Thunderbolt, disconnect the power, and now I'm going to go through and get myself a DMM and we'll get that hooked in. All right, so things are plugged in mostly, but I wanted to give you a little bit of a sneak peek. So now I've got my ability to have my oscilloscope immediately next to my DMM within the same system. So once again, I don't need to use them both at the same time on my debugging, but boy, sure isn't it nice to just have a scope and a DMM, once again, benchtop that works for your debugging purposes, but then also can be used all the way out to validation, characterization, and production as well, as opposed to maybe a handheld job that you're not going to go ahead and be able to create the same automation and software for. So let's go ahead and get this plugged back in and we'll try. All right, so I'm going to do that same thing I did last time, hardware configuration utility, and we're going to go ahead and launch that and make sure everything shows up well in the system. All right, we're in luck. Here we go. So we do indeed have not necessarily our latest and greatest equipment here. We've got an older generation, just actually a first generation PXI 1072. We've got actually mixed modules in there. So we've got our multimeter and our oscilloscope now available within the system. I'm actually going to go through here and actually open the software panel just as we had done before. And then I'm going to go ahead and open up the other one too. All right, you can see that we've got our multimeter readout here, trace live. Let's go ahead and see what that resistance is on that device. So or actually just that simple potentiometer. Now, of course, there's a bunch of different ways I could have done this. I could have gone through and just set a strong voltage across it and measured the voltage drop using my oscilloscope, but we're gonna go ahead and do it, let's not say the hard way, but just the different way. So we're gonna go ahead and pop that out. We're gonna pop that into there, across from there to there. Good old-fashioned engineering fun. Oh, that's right. Sorry, I need to go ahead and change it over from a DC voltage to a resistance. Let's do 2-wire resistance. All right, so we see that we're at about 600. Let's see. All right, so we're seeing some decent variability as things warm up. Now, the twist is also in instrumentation, you should probably let all of your instruments warm up for a good half hour ahead of time. I just slapped this in there and off to the races. So, but indeed, after a little bit of settling, probably me wiggling this a little bit too much. Yeah, as you can see there, as I move things around, we're looking at a few ohms different. But we're at about that 640 ohm range to go ahead and get that. Now, if I go ahead and I turn it up just a little bit, yeah, you can see it goes basically to 1K with a little bit of modification. So maybe if I can find myself a 1K ohm resistor, or maybe 3 of them, I can set them all in parallel. Is that the math right? I got to think about the math real quick. But that's about where we've got on the overall resistor. Let's see what we can find to put in system to go ahead and act as those pull-up resistors. All right, another quick thing worth noting, once again, learning how to do things within our equipment. One of the things I noted here is that I needed to change it from the auto ranging to something explicitly set. So let's go ahead and take that, and we want to take it directly to, we want to be less than 10 k ohm. So that's kind of what we're going. I know that the one that I was just looking at was a 10 kilo ohm. So we're going to go ahead and leave it at that. Let's go ahead and probe it and see what that signal looks like. Of course, once again, as I just manually drag one of these over it. Yeah, so I've got a 10K ohm resistor, just a little bit under 10K ohms. Let's go ahead and get that there. Now, of course, I could drop 10 of them in parallel, and that would get us a little bit closer, but that's not really what we're looking to do for this experiment here. Yeah, so we're not quite there. Let's see what we can do in terms of continuing to dig through my bag of resistors to go. All right, everybody. So as it stands right now, you can see once again some beautiful wiring here. Pun or not being serious on that one. But we've got our basically our pull-up resistors here. I'm going to do an experiment. I've got a 1K ohm resistor that you can see right there, and then three 220 ohm resistors, getting us closer to that 660 that we were looking at before. Obviously, nothing is beautiful or crafted all that well here, but we're going to see what we get on the other side. So let's go ahead and see what we've got with our let's see that split screen right there. There we go. So we're going to go ahead and leave that as is. That way some evidence if the magic smoke comes out of the screen. Let's see what we've got. So I'm going to go ahead and get connected into our oscilloscope again. I'm going to go ahead and put our oscilloscope on the screen. We've only got one in the system. We're going to go ahead and get that configured again. But let's go ahead and see if we can make sure that this works. All right, we've got our system, we've got live data indeed coming in through the thermal camera. Let's go ahead and see what we've got on our oscilloscope, if we've got anything. All right, so we're back in business. This is great news. All right, so what we're seeing here is basically both signals. I need to go ahead and change my trigger source over to that trigger one with that window for leaving that window and set those ranges again. Let's go ahead and get that window interactively configured. All right, so that's pretty close. We're seeing a little bit of jitter there. I think I know what the reason is why it's doing that, but in all intents and purposes, we are a lot closer than what we had before. Let's go ahead and see what we need to go ahead and look at a larger time scale. I'm going to use that mouse functionality to just kind of scroll around. So figured out part of the problem is that by cleaning up the signal, I lost the ability to set that very specific trigger edge. Now, some of the things that we can note that's probably pretty important at this point is that this oscilloscope is missing some features that I would really, really like. We have higher end oscilloscopes that basically have a kind of a trigger range, kind of almost a hold off, that it needs to be outside of a range for a certain period of time. This oscilloscope that I'm using here doesn't have that feature. Of course, every oscilloscope is going to have its own swath of features, so we're going to be somewhat limited to that capability. But that's where the power of actually having basically a computer-controlled and computer-connected instrument is really going to come in handy, because what we can do is we can flip over into automation. Now that we know that we can kind of debug the signals, and we're going to create a very simple program to just get a long records acquisition that's going to give us the ability to kind of tweak with signals after that fact. And so let's see what that looks like. All right, so I've been fighting this beast for quite a while now, and let's just get real. There's no way I'm going to be able to go ahead and figure out how to get this triggered as everything is currently configured, mostly because I'm using an oscilloscope that doesn't have the feature that I need. And the feature that I need is highlighted here on the screen right now. It is the with triggers. And so basically it gives us the ability to go ahead, and it's available on our higher end scopes like our 5162. This is an older generation, but what it would allow us to do is go ahead and say only after a very certain period of time has been established and there's a falling edge, at that point in time, go ahead and basically assert whatever trigger that you see, which would work great in our situation. It just happens to be that's not the oscilloscope that I've got. But really, what am I trying to look at this point in time? Really, I've used my oscilloscope, my PXI-based oscilloscope going into a Thunderbolt chassis into my laptop to figure out what I need. Right? I've got the ability to set up and configure and compare the information. And let's go back and look at that, basically both of those traces as they go. Now it's a little bit jittery, and so I'm going to go ahead and basically do a single acquisition that you can see there. And you can see that basically now I'm looking at my overall signals. I can look at my data after the fact. Once again, just kind of interacting with the computer with the scroll wheel. Very useful, bringing the best of both your benchtop scope and also a computer-driven system that we've got here. And we can see some of the information. We can see that basically our blue trace is the one that has the 1 kilo ohm resistor, and the one that has about the 660 ohms worth of pull-up resistance in line here has a bit of a sharp edge. It's a little bit more, it's very clear that's a much stronger configuration for what we've got. Now, the problem, once again, as we had noted, is that by doing so, I've lost the ability to kind of have that, that edge, because there was originally a bit of a drop down as the microcontroller was actually pulling that circuit low. All right, so we're missing the ability to go ahead and get that information. So what's the idea? What do we do now? Well, the reality is I can get this information and I can acquire a very long record and then pull it into LabVIEW to go ahead and do the further analysis on it if we so chose. So let's go ahead and walk through how would you deal with, basically I have an inability to look at the trigger live on the oscilloscope, so let's go ahead and get it into software. Well, first things first, I can go ahead and set up a very long acquisition here. I'm just going to go ahead and allow that to run. And I'm going to go ahead and modify basically my acquisition by clicking that. And basically, sorry, just keep repeating basically. What we're going to go ahead and do here is look at this signal. Let's just go to the screen. And we're going to go ahead and set basically a manual override on most of the settings. And I'm going to go ahead and say I want to take maybe 10 times the amount of data that I've got there, which is quite a bit, but it's going to give me a bunch more acquisitions. The other part is maybe I can tune down my sample rate to maybe 10 megasamples a second and still see a pretty reasonable signal. And so we've done that. You can see now our sample rate is set to 10 meg. That looks pretty good for what we were looking for. We've got a long record so we can see multiple acquisitions, but let's go ahead and even bump that up. Let's go to 5 times that amount that we've got there. Now that's going to be a really, really long acquisition, but now what we can see is we've got the full acquisition happening up top. We're looking at a very bitty slice of it right there. That's fantastic. That's exactly what we need. So let's go ahead and stop it because it's really chewing on the system a bit here. And we should be able to right click, export basically the driver configuration to disk. And now what's going to end up happening here is by exporting this to disk, so now what we're going to have the ability to do is go ahead and basically do this exact same acquisition in our programming language of choice. Of course, in my case, it's LabVIEW. The other thing that we're going to do is we're going to go ahead and export the actual data that we've got here. And I think it's this right there. It is capture data. And so that should actually save a screenshot and then a snapshot of all the data, and we're going to be able to pull that into LabVIEW as well. So let's go ahead and see. Yep, we've got an image right there. Let's go ahead and click on that, and that's going to be able to show us what we were looking at on the screen, just like you would do on a given oscilloscope. And we should be able to go ahead and click on our capture over here, and it's going to go ahead and open up our default TDMS viewer known as DIAdem. Now, for anybody that has the LabVIEW Plus suite or has it as part of kind of their agreement that you have access to DIAdem, I think you even get a free viewer nowadays as well, you should actually be able to go ahead and just double click on any TDMS and we can start to look around. Now this is the interface for DIAdem, and it already loads basically all of the data of interest into the data portal. That's that section that we have available over here to the right. Now we're going to look at a view that we already had. We don't need this. We don't need to see any more burning of Oreos. If you're curious about that, go ahead and check out my other channel online on YouTube. But we're going to go ahead and make a 2D axis system. We're going to select those 2 scope channels from over there in the data configuration, and you can see that we're just looking at that small snapshot of what we had available on the screen, not the entire acquisition. So you might say, oh, wait a minute, what happened to the rest of it? Is it there? Can I even get that so I can view it once again simply in DIAdem? And the answer is yes, it's actually not that difficult. You just need to go ahead and kind of zoom out as it was on the display. So let's go ahead and pause this for a moment. We're going to go ahead and kind of minimize DIAdem. Actually, let's go ahead and we can just remove these channels so that we don't get confused when it loads next time. All right, so those data elements are now gone. And what we're basically going to do is zoom out on the graph that you see here. And what you see very quickly is indeed, as we zoom out, we're going to see larger and larger amounts of data. It's not acquiring a new data set, it's just taking what has already been acquired and allowing us to kind of zoom and navigate around it. And at some point in time, it's going to reach that upper limit. I think there is a maximum divisions that the tool has to be like 20 milliseconds per division that's allowed here. And so, of course, it's going to kind of trim off those upper edges. And so, but it's still giving us a much larger view of what we had before, for which now if we were to go ahead and do that same thing and do data, capture data, it's going to give us a new list down here for what we can see. Double click on that TDMS. It should open up again within DIAdem, and then we can go ahead and browse around that same larger set of information. So there's DIAdem loaded. Let's see what we've got here. Is it loading up in the background? All right, so it looks like it didn't automatically snap into existence over there, but another neat feature that I can show you is that I can go ahead and right click on the data set itself, locate in Windows Explorer, and then now if I kind of get DIAdem visible at the same time, I should be able to go ahead and drag and drop that into my data section, copy and paste both of those. You can actually see the preview down here in the bottom, which is another great feature of DIAdem. So I can see that I have both of those data sets available, drag them into the field here, and I should be able to look at a much larger data set that you can see that now we have everything available. And DIAdem does a really great job kind of chewing up and spitting out all that data that's available. Actually, y'all didn't even see that. Hold on, let me go ahead and just show the screen. So, sorry, I had my fat head in the way. But you can see down here in this bottom section that there's a little snapshot of those individual channels, so you can kind of sanity check before you drag them up onto the graph. And so now we've got the ability to kind of look through that data set, and we can use the cursors to do the same type of thing that we were wondering about before. Actually, let's go ahead and see if we can get in real tight on these cursors, and we might be able to even just do a quick analysis to look at, let's go ahead and we can turn off the data, and we can just go ahead and look at the clock itself and see if we can go ahead and put some banded cursors up there. All right, so I was able to pull up the analysis cursor. Actually, that's a feature that you can see up here, which gives me a bit of details about the position of each of my cursors. I'm going to go ahead and zoom in on the section that we had available there. Actually, let me just go ahead and choose the banded zoom here. Let me go ahead and see if I can get that. All right, so there's my banded zoom. I should be able to click on that and now zoom around in that range. Let's go ahead and do that again. Actually, let's get those cursors where we want them to be, basically closer to where those clock edges are. And now we're going to go ahead and get in tight on that and zoom in. All right, so we've got them available there. Let's go ahead and get them in the territory of what we're looking for, and we're going to zoom in. So let's go ahead and get that there. We're going to get in tight. There we go. Now we can see those clock edges, and we should be able to move those into the territory of interest. And we're going to basically, we should have a 400 kilohertz clock edge. And let's go ahead and actually, let's get, once we're already in there, kind of go ahead and move some of the data set around. Fantastic. All right, so if we were to look in here, let me see if I can zoom in on it. All right, so I've got my cursors inverted, but you can see that if I were kind of put an extra notch there, and we don't have to worry about that, but we are very, very close to what we would be looking for overall. So it was supposed to be 400 kilohertz. We're at 370. It's about a 10% error. So that's not the best, but it's still, we know that we're looking at the right set of information for what we've got. So let's go ahead and figure out what to do from here. Now that we've got the data, we've exported it, we can see it in DIAdem. Now the twist is we want to be able to get it into LabVIEW to actually unleash the power of all the processing that's built into it and show you how quickly it can be done. Okay, so we're back into LabVIEW. We're looking at our code. It's still running as before, so that's good. We're just going to go ahead and make a new VI and see how quickly you can go from basically no program in this few lines of code effectively to go ahead and get that same information and then kind of continue to like look at it, visualize it, and continue processing. So on the block diagram, we should be able to go to our scope. If you go to measurement, and you should be able to go to NI scope, as you can see highlighted there, and we're going to just pin that down, and we're going to start dropping modules to go ahead and figure out how do we get to that configuration and get to our data fast. So first and foremost in the system, we're going to drop the initialize, and another really, really handy feature that we've added in recent versions of all of our drivers is the ability to import and export in the entire configuration in a programmatic way. And then not only import it, but it also allows you after the fact to tweak it. So if you remember, we exported that configuration previously, and now what we're going to go ahead and do is do that. We're going to import it. We're going to import it from file, and then I believe the other part of it is basically from there we should be able to initiate and go, or actually I think we might even just be able to put a read and then a close afterwards. So let's go ahead and see what we've got here. Let's drop that into Control-Shift-W. This is a great little feature of LabVIEW. If you have it available, it allows you to kind of link all of those calls together without any effort at all. You can go ahead and, if you Control double click as you're wiring, it'll make a constant. Now we've got our scope that we've named in the hardware configuration utility. We're going to do the same thing with the file path. And then it's a constant on the diagram, but this is one of the beautiful things about LabVIEW is that it's data smart. What are you going to do with that data? Well, I know that I need to browse for the path to that data. So let me go ahead and click on that, and you can see I've got the NI scope configuration saved in front of me that we had just a moment ago. Now it's set as the constant on the block diagram, and I should be able to basically do, let's just do DMC graph. Oh, it looks like that's not available. Let's do graph silver. There you go, waveform graph, silver type. Let's go ahead and make it a little bit big. Actually, we're going to do, we're going to create a couple things. We're going to make sure that the visible items of the graph palette, so we kind of get the zoom tools available. And I'm just going to do a thing that I love to do of just, let's just make it the whole dang size of the screen as it is right now. So now I'm going to go ahead and wire this up. I'm going to go ahead and get the channels available here, 0, 1, so we get both of them. And then I'm gonna put the waveform out on the other side. Now it should be multiple waveforms, and we're gonna do the 1D cluster. And if I run this one time, it should give us a waveform out on the other side. Ah, fantastic. Shouldn't be too much of a surprise, but it is always nice to see when you create something that it just works for you. So we have it available, we have it visible, we can run it again another time. Now it's grabbing a whole half second's worth of data. So if I were to go through and actually just put this right here into a while loop, let's do that, a while structure, WS as quick drop has it. I'm gonna create a stop button on it, make sure that that shows up on the screen. Let's go ahead and move that up. That's one of the slight issues of when you go ahead and add new things and you maximize to the screen. It's gonna show up off screen with that one, but I'm used to that. So let's go ahead and run that one time. And now it's running, 1, 2. So there you go. So it's about 2 updates per second. It doesn't look that fast, but of course we've got a half-second update right here. But indeed, we're getting the data set out of it. And if I were to zoom into that 0 section right there, actually, let's turn off that auto scale that we've got. And there you go. Now you can see that we've got our trigger set. It's kind of flickering a little bit, unfortunately, once again, because of the limitation. But you can see that we've got such a large data set available here. And if we wanted to, we could basically turn the screws on the driver and just open it up and get multiple seconds worth of driver until we fill up the memory, or we can even set up a streaming application to constantly dump this to disk or even process it continuously. 2 great features of having an oscilloscope that acts like not only a scope with all the interactivity, but also just a high-speed streaming digitizer to the rest of your computer. So we've got it available in LabVIEW, and let's go ahead and look at what we've got. It's basically 3 functions to get your data in a 4th one with the close on the output, just to make sure that you're doing it right. So really no effort at all to go ahead and get the data, get it configured, locked into the instrument, and then start getting the information that you need out on the other side. If you want to go deeper on the driver and figure out how to stream and how to do more with it, or how to process the data, or even look at the clock rate, we're going to save that to a different video just for the sake of time for what we've got right now. So one last thing to note is that we're underneath automation here. And it used to be with NI equipment and modular instruments, once you started automating, you lost that interactivity, you lost that update on the screen. And that's not what we want. We want to be able to see that tighter information. So let's go ahead and let this just run and see what happens in Instrument Studio, because we didn't close it out. And so we're back in Instrument Studio, and one of the things that you can very quickly see is we're not seeing any updates. But don't forget, we've kind of gone beyond the bounds of a traditional scope where it kind of auto-tunes a lot of things for you. We're using it a bit more as a digitizer now. And so you can see up here in the upper right-hand corner that it's actually throwing a warning at us that indeed the monitor mode, like so while the automation is going, we have a restriction on the overall what we can see update live. And that's because we prioritize automation. We prioritize that overall performance of the speed of automation over the ability to just kind of see the data. Because we presume if you need that data and you're getting that much information, you're taking care of it in your program. However, a few different things that we can do to kind of get back to viewing the data if you're doing some form of automation is to just go ahead and pause that automation. So you can see, and we still have it going there, it's still doing the automation, but now as we come back into our oscilloscope, we can go ahead and take control. It's kind of like hitting the local button on the screen. And it's not all that dissimilar. So now that we're in the process of controlling it, it's going to start doing that acquisition that's very, very long, but really we don't need to see that many milliseconds per division. So let's go ahead and adjust that. So it's something, I think, what was it? We'll go to that 5 milliseconds per division now. And now we should be able to see those updates a lot faster because we're not necessarily in monitoring mode anymore. We're kind of in that debug where our program has paused. Now, if we really wanted to do this smart way, the right thing to do would probably be to not do such a massive acquisition in one fell swoop, but to do a continuous stream of information for as long as it mattered to us. And that would be one specific way of doing that. And so we've got that, and now we can go ahead and zoom in. And then really, once again, it's not changing the acquisition, it's just changing the view that we're seeing from within Instrument Studio. What we're going to do now is we're going to go ahead and basically kind of stop the acquisition here. We're going to go ahead and set it to single so it just does that one longer acquisition, and then go back to the automation so that we don't try to reinitiate while the soft front panel was also doing what it was doing. So let's go back here and continue the process of acquiring, and you can see that our data indeed is live. And so while it's very desirable for me to keep going and to try to start creating algorithms to go ahead and segregate the bursts and figure out the clock time and kind of decode the digital information, We've been going for a while, so I appreciate your attention. Okay, so quick recap. What is all the territory that we covered? So what did we do? Well, we started out looking at our design with my kind of shoddy wiring job and figured out I probably have some issue with my signal integrity. So we got our PXI chassis, a little 2-slot Thunderbolt, that's the 1090, put an oscilloscope in there, 2 channels, and we cabled over to the system. Of course, I had to flub around with the impedance or the proper attenuation on my probes, but we got that figured out, got it in there, saw that we had some signal integrity issues, and we needed some pull-up resistors. Then we did a little bit of experimenting with the pull-up resistor to figure out maybe about what point we've got this nice balance between low-end bias and sharp edges. And at that point in time, we knew that we needed to go ahead and figure out what is the right resistance. And we were able to add into our PXI system very easily a DMM. We probed it out, we put it into resistance mode, and we were able to figure out what is the resistance of that was going to give us the best performance. Did a little bit more shoddy wiring and got those other resistors in the system there. And then we wanted to look into the actual signal so that we could continue to do maybe more processing to figure out maybe if there's glitches in the information, if there's dropped bits, or if anything else in terms of the system was causing problems. Well, we could continue to do that interactively through Instrument Studio, but by being able to save that configuration and save the data, either to look at through DIAdem or to pull into your programming language of choice. Of course, LabVIEW is going to give you the fastest way of doing that to go ahead and, once again, get it attached to your hardware, get a configuration loaded, and start to pull that information in. But we're not just dumping it off into a CSV file with LabVIEW, and that's the great part of working with a programming language that was purpose-built to make your signal analysis and what you're trying to do faster. We could basically very easily point it at the instrument because the driver was installed. We had examples and exercises to go ahead and do that. And then all of a sudden we were able to load the configuration, we were able to fetch it into a plot and see it and interact with it right away. And then also on top of that, we were able to still link into that interactive experience if we needed to go back and forth between automation. All right, so that brings us to a wrap in a lot of different ways. So there's a lot of content that we covered, but hopefully you feel more confident being able to take basically your electronic device design and to be able to use NI equipment and NI software in LabVIEW to be able to accelerate your debugging process, get you access to the data and the insights that you need fast. And so be sure to join me next time when we dive into more topics accelerating your engineering time and time to insights with LabVIEW and with NI. Thanks.